engine crankshaft is always going faster than the propeller, because we can't have the propeller going the same speed as crankshaft, because the engine's going too fast. We would end up with tip speeds of the propeller reaching sonic, which would be the speed of sound, and we certainly don't want that. Okay, that would make it probably disintegrate or fall off or something. Too much stress on the propeller. So by using a reduction gear, we can have a lot of torque, a lot of power there, but without overstressing the propeller as well. Okay. So as we go through the next few books, we'll look at control systems, how it does it automatically, and how we can control that manually as well. Okay. So now we're going to move on to propeller efficiency. So we've got another formula for you. Just to, first thing in the morning, we've got a formula, just what you need. All right. It's not too bad though, so bear with me. Let's get going. Power efficiency. What is it? So it's efficiency of any system can normally be measured from a ratio. Again, we're looking at ratios, so it's going to be formulas. A ratio is also known as a coefficient. So we're looking at power in and power out. And the power extracted from propeller, the system is a product of force times velocity. Going back to basic physics, P for power equals force times velocity. All right. So I've got things just to remember there. Or it could simply be, in our case, thrust, which is the lift provided by the propeller going round, multiplied by the aircraft total airspeed. So this time we've indicated the airspeed, now we're looking at total airspeed. So thrust multiplied by total aircraft speed. Power put into the system required to overcome rotational drag. Unfortunately, yes, as we get lift and thrust from a propeller, we do induce drag. We can't get away from that. No matter how good the design of the propeller is, we're always going to induce some sort of drag. So therefore, that's a product of the propeller force, okay, torque in this case, propeller torque, the force, multiplied by the speed of rotations or rotational velocity. And propeller efficiency can also be a ratio of thrust multiplied by 2 airspeed, your power out, okay, to the ratio of the torque times 2n. Now, n means the number of revolutions, power in, or angular velocity in this case. Okay, so angular velocity, because we're going around in a circle, if you go back to your module 2 days, that'll probably seem like physics like years ago. We've got the angular velocity. So in a circle, you've got your angular velocity, say that's the tip of the radius. There's your angular velocity going perpendicular to the tip of the propeller. That's your angular velocity. Okay, so we've got a little formula there. Now, the power output in a propeller system is supplied by the engine, and is therefore the brake horsepower of the propeller shaft. Okay, remember what I said about brake horsepower was yesterday. That is what is left from indicated horsepower. Now, indicated horsepower is the theoretical perfect horsepower you should get from an engine, but once you add the propeller on there, once you add friction and all that good stuff, resistance, you lose a bit of power, and the brake horsepower is what is left. So therefore, excuse me, propeller efficiency is simply thrust horsepower divided by brake horsepower. Okay, thrust horsepower divided by brake horsepower. Exam-wise, you might just get what is the formula for propeller efficiency, and that was just what you'd have to remember. Okay. So with an aircraft stationed on the ground, propeller efficiency must be 0 because it's not going forward. Although considerable thrust might be developed, you get no useful work done. Yes, we're getting thrust from the propeller sat on the ground, but it's not pulling the aircraft forward, so it's not efficient. It's not moving yet. So we class that as no work done. So therefore, efficiency will increase once you get forward speed and may reach a peak of approximately 80%. You never ever get 100% efficiency. Why? Because us humans make things, but not perfect. We cannot make anything 100% efficient. We'll get very close, and we're always striving to do that with better materials, better products, and better manufacturing processes, etc. But a propeller will get about 80%. The better the designed propeller, the more efficient we become, but we will always have drag, so we'll never get 100% efficiency. So 80% is pretty good, but we'll always try and get better where possible. So remember yesterday, the most efficient part of the blade is approximately, do you remember the distance? Anybody?
2 by third and third by quarter.
Yeah, 1 3/4 of its span, good. Okay, that's the the main part of the blade. As it gets past that, the blade gets smaller, so we can stop aerodynamic losses. So about 2/3 to 3/4 of its span. Good. So comparative engine operational propulsive efficiencies. Bit of a mouthful there. What is it? All it is a comparison between the type of aircraft we got. In your graph in your book you've got here, along the bottom we've got airspeed and miles per hour, and we've got propulsive efficiency. So let's look at a turbojet, so in the blue line here. So basic gas turbine engine. It's pretty much linear all the way up to almost 1,000 miles an hour, depending on the aircraft obviously. It does start to drop off a little bit, but propulsive efficiency is far steady all the way through. But at low speeds, if you look here, it's only about, what, 25% efficient? Compare that to a bypass aircraft, then you compare it to a propeller, a turboprop. The propeller at low speed is about 60% efficiency at 200 miles an hour. We got to about 400 miles an hour. It's now starting to drop off though. We can get, what's that, about 350 miles an hour. It's approximately 80% efficient. Compare that to a jet engine, which is only about 40% efficient. So the jet engines, like we saw yesterday, it lets go faster and higher, where a propeller engine only lets go slower speeds and lower altitudes. But it is far more efficient at lower altitudes and lower speeds. Hence why I use propellers in that sort of area. Okay, but certainly higher speeds, we become more efficient for a turbo engine. Okay, again, we'll learn about that more on module 15. So that's just a little comparison between a propeller, bypass turbojet engine, or a pure jet turbojet engine. Okay, what I mean by bypass engine is we have air. A bypass engine, especially in a commercial aircraft, which are high bypass engine, it is what it sounds. It bypasses the core air. You basically propeller on the front, but it's not a propeller, it's a fan encased in a casing, and we call that bypass. And it is the cold air from a bypass engine that actually provides about 80% of the thrust. Okay, but again, don't worry about it for the moment, we will learn more of that in module 15. Okay, but certainly for low speeds and more efficient, we tend to use a propeller engine. Okay. So look at a variation of thrust efficiency with forward speed. So if the blade angle is fixed, we've got a fixed propeller, the angle of attack will change again, like we saw yesterday, with the variation forward speed. So if the aircraft goes faster, your angle of attack decreases, and likewise, if the aircraft slows down, your angle of attack will increase. Okay. It's the same as what I spoke about yesterday. Okay, so yeah, speed increases. Oh, coming in. Speed increases, the angle of attack decreases, and with it, the thrust obviously as well. Okay. The effective thrust efficiency is at high speed, the angle of attack of the blade will be close to zero. Zero lift and thrust will reduce to zero. Therefore, propeller efficiency will also be as close to zero. Okay. So in other words, remember high speed, it's catching up with the relative airflow, so angle of attack is quite low, so efficiency is quite low. Lots of torque, yeah, we've got a propeller going quite fast, providing lots of torque, but not being efficient. It's not pulling that aircraft forward. There will only be one speed at which a blade is operating at its most efficient, and its most efficient angle of attack. Therefore, efficiency will be at its maximum. That will be dependent on the aircraft type, the engine, the type of propeller that's being used, or propellers. There could be multiple propellers on there. So at low speeds, thrust increases, angle of attack, and provided the blade is not stalled, thrust is very large. We want to increase that angle of attack as much as possible to get as much power, but without the possibility of stalling at the same time. But therefore, the speed is low, and unfortunately, efficiency is low as well. So looking at that, there's a little graph showing you what's going on. So at low speed, okay, relative airflow coming in, the angle of attack is quite high. All right, at low speed, so it's getting there. It's maybe not quite efficient. It's quite a lot of thrust, but not quite as efficient. Optimum speed is somewhere in between, so the angle of attack is a little bit less now. And at high speed, obviously, the angle of attack is a lot less. Okay, so the optimum speed is somewhere in the middle here. All right. So the faster it goes, the change in effect and thrust will be. Now we're going to move on to what's called geometric pitch. So the geometry of the pitch relative to the actual propeller as it goes through the air, depending on the angle of attack of the actual aircraft as well. So what it is, the distance the propeller moves forward in one revolution without slip and is measured in inches. And what we mean by slip is, in theory, the tip of the propeller will move forward one revolution like we saw yesterday in the helical variation, but unfortunately because of drag due to the aircraft size, the propeller's trying to move through, but it's actually, as we pretty much says, slipping through the air. It's not quite getting to where it should be, and we'll look at this in a minute. A theoretical distance calculated from the blade angle and propeller radius at a particular blade section. And it can be compared with what's called the screw thread lead. So if you get a bolt, you put it in a hole, and you screw it in, it should go as far as it is on the one thread, okay? But unfortunately, because of air pushing the aircraft back, it doesn't quite go that same distance. And the actual formula for that is geometric pitch is 2 times the radius times pi times tan. Just be aware of that formula, okay, at the moment. But we'll give you an example coming up. Fixed pitch propellers are classified, and it's a good one to highlight in your books. Fixed pitch propellers are classified by diameter and pitch. So in other words, the size of the disc the propeller makes it spin round, and the pitch as well. Okay, that's how fixed pitch propellers are classified, because we can't change the pitch. We can have various fixed pitch propellers. We might want to fit a propeller to an aircraft that's just wanting to not fly very fast, but it wants a lot of power and torque. Or we want a fixed pitch propeller that it's got maybe a coarser pitch that might take a bit longer to take off, but it's more for cruising at slightly higher altitudes. Okay, you've probably seen some of those stunt planes that the Red Bull races. They're flying very quick in and out, very low level. Well, they've got a very shallow angle of attack. They want all the power, they want all the torque there and then. They're not going fast. Well, they are going fast, obviously, but not as fast as we do maybe high level for cruise. They just want very quick, sharp, maneuverable aircraft. Give an example there. So, effective pitch or advance per revolution. Its actual distance, the propeller moves forward one revolution and is affected by, obviously, aircraft flight conditions. For example, if the aircraft's flying into a headwind, as the propeller's trying to spin forward and pull the aircraft, it could just be spinning where it is. There's a very strong headwind. You can, in theory, get a point where the aircraft's almost stationary. It's just flying like that. It's just hovering like a hawk sort of thing. The propeller's corkscrewing through the air, but it's not pulling the aircraft forward. And likewise, you get a tailwind. Aircraft, as it does one screw, it's actually going quite fast with the actual rotation of the blade. So it can vary with conditions. The size of the aircraft, if it's the aerodynamics of the aircraft can affect it as well. Now, effective pitch may vary from 0, small attack, when the aircraft is stationary on the ground because it's not pulling the aircraft, and up to approximately 85%. We said about 80 to 85% of geometric pitch during the most efficient flight conditions. Ideally, it would be 100, where for every one revolution of propeller, it gets to its point where it should be in theory, but we never get that due to drag factors and conditions. So slip. Slip, this is the difference between the geometric pitch and your effective pitch. Think of you've got a clutch in your motorbike or your car. You've got the engine running, you let the clutch out a little bit, but it's actually slipping. Your clutch is slipping until you let the clutch fully out on your motorbike. Once it's full out, then you get the full movement forward. Okay, roughly a propeller slip is similar to that. Until it catches up with itself, it doesn't get there. But what we have in the aircraft is purely drag factors, aerodynamic factors, and climatic factors as well. In effect, it is a volume of air. So we have a little formula again. So slip equals your geometric pitch minus the angle of advance revolutions divided by geometric pitch multiplied by 100. So just make a note of that in your books at the moment. It should be on page, I think, 67. And we'll do a little example of that coming up. So there we go. If a propeller has a geometric pitch of 50 inches, in theory, it should move forward 50 inches. In other words, as the propeller starts, oops, change the pen. Try again. Advanced graphics tablet is the pain in the back side. Let's try and move it. So, in theory, as it screws through the air like that, from this point here to that point there, as the propeller spins round at one complete revolution, it should move 50 inches, okay, in theory. But because of aerodynamic losses, drag, we will probably only get to maybe round about this point, okay, once it's actually done one full revolution. So the tip of the propeller blade will spin round, but it might only get as far as there. That's how far it's dragged the aircraft forward. Okay, maybe about 80% of that. So we'll work this out. Nice little figures we'll use. I'll show you what I mean by that. Okay. So, if the propeller actually moves forward 40 inches, what is the slip expressed as a percentage? Okay, so in theory it should move 50 inches. It's come forward 50 inches from one revolution as it corkscrews through the air, but it's only gone 40 inches. So what's that as a percentage? Now you could do just basic maths as well, or we can do it like this. You've got your theoretical number here, which is the 50 inches, but it's only moved 40. So it's simply 50 minus 40, multiply that by 100, then divide by 50. Or you can do it 40 out of 50, or 40 divided by 50, and that will also give you 20%. That means we've lost 20%, okay? Or I can do it the other way, 40 out of 50 is simply 80%, okay? So the propeller, in this case, has been 80% efficient. If it moved through 50 inches, then yes, that would be 100%. We'll never, ever get that, unfortunately. So the greater efficiency, the less slip, the more efficient the propeller is becoming, all right? Everybody sort of understand what's going on there? Any questions? We calculate how much the propeller rotates and how much distance it gets. In theory, what it should get, but we actually calculate what we actually get in the end, the real result. So in this case, this propeller was 80% efficient. We lost a little bit of slippage, but it wasn't too bad in the end. So there's a diagram of what's going on. So your geometric pitch, so from the tip of the blade, as it rotates one full revolution, using the previous example, that distance there would be 50 inches. However, the effective pitch, as it went through one revolution, it got to that point, which was 40 inches. So it's the distance between here and here, how much we've lost, worked out as a percentage. In other words, how far it's moved that aircraft is only there instead of there. Okay, we'll never ever get geometric pitch. Okay, it will always be the size of the aircraft, the drag factors, and that sort of thing. So geometric is the theory, effective is your actual difference between the two, is the distance, and then convert it to percentage. Okay, you might get asked a question like that in the exam. Again, the numbers that we put in is very, very simple. There won't be large numbers, so you won't need a calculator. Okay, you don't need a calculator for any exam. Well, certainly, if they do put a question like that in, it will be quite straightforward, hopefully. Any questions on geometric and effective pitch? Silence is good. I like silence. Well, don't. It's nice to see people talk back. And you've all put your cameras off. Don't be shy. Keep your cameras on. All right. It's very lonely looking at a blank screen. Okay, let's move on then. We're going to look at what's called swing on takeoff. Swing on takeoff. Now, we spoke yesterday about the opposite effect of the engine. The engine rotating one way, so it's trying to rotate the aircraft the other way. Now, as the aircraft, it's an aircraft, propeller spinning, it's pushing air backwards. Now, that air doesn't just come straight backwards over the aircraft. The air is corkscrewing, just like the propeller. Excuse me. Oh. Right, so there's a tendency for propeller aircraft, or driven aircraft with a tail wheel undercarriage. So you imagine an aircraft sitting down and this little tail wheel at the back, the undercarriage here, to swing to one side. One point it's trying to rotate the aircraft, but the actual airflow coming backwards over the aircraft will try and blow past the fin which will try and move the aircraft to one side. Now, if it moves the aircraft to one side, we're going to get a yaw effect. So there's a chance that as you take off, it could actually yaw and go sideways up the way as well. Hence why, obviously, you have to be trained to be a pilot. Always makes it handy, you know. So the causes of the tendency are what we call asymmetric blade effect. So we've looked at asymmetric airfoils and modulate. We looked at symmetrical airfoils and modulate. Now, asymmetric has a slightly larger camber than others. Because of the wind shape that's coming over from the propellers, we got an asymmetrical, what's called blade effect, because the propeller blades are asymmetrical. They're not symmetrical because they wouldn't give you much lift. They are asymmetrical. Torque reaction, yeah, the actual torque of the aircraft and the rotation of the engine. And the slipstream effect, as I say, as the air comes back, corkscrewing back, twists over itself, and causes a few complications. And good old gyroscopic effect as well, from back to your physics days. So, in propeller-driven aircraft, the tail wheel, the propeller turning anti-clockwise. So if you're looking at from the cockpit, and the propeller's going anti-clockwise, when viewed from the rear, all the causes above that I just mentioned there will act in the same direction. So some aircraft configurations compensate that. The factors, they'll use a nose wheel type of undercarriage to compensate for that. Or they might even put contra-rotating propeller, so propeller behind the propeller on the same hub. Again, that provides a lot of weight, but by contra-rotating propellers, then that cancels each other out. So the airflow and the gyroscope effect, the torque effect, all cancels each other out. Okay. And maybe some biased directional trimming. So you might actually have a trim on the back of the fin that's in one direction that counteracts the forces trying to move the aircraft in the wrong direction. So asymmetric blade effect. Effect arises from the axis of rotation being inclined. Now what I mean is that instead of the aircraft level, the actual aircraft is inclined. Now, normally it is, yeah. Your wings got an angle of incidence about 2 to 4 degrees, but as the aircraft sits on the ground, some aircraft are pretty much level. That's fair enough. That would be your nose wheel steering type aircraft. But the aircraft got a tail wheel tend to sit a bit of an angle, don't they? As they tax out, they tend to sit at a bit of an angle. So with the inclination of the propeller, then that's changing the torque and reaction as it flows back away. So this is what I mean by here. Obviously, if this aircraft was horizontal, we'd probably have a nose wheel here, but because it's inclined, as this propeller blade comes down the way, it's closer to there, but as this blade goes up, it's further away. So that's changing an angle of attack in effect. Okay. So what do you mean by that? So angles of attack and velocities are changed when the axis of rotation is inclined. The downgoing blade has a higher angle of attack and therefore produces more thrust than the upgoing one. Because of the profile shape of the blade, as this one is coming down the way, it has an increased angle of attack. Okay, got more oomph behind it. But as it's going up the way, the profile is now changed, so it's got less angle of attack. So there's more power coming down, as I said before, on the anti-clockwise side. Okay, but provide more thrust. Well, it's more thrust this side, then it's going to try and spin the aircraft around. Okay, if it was straight, it's sort of balanced out. The angle of attack would be the same for both of them, so that would balance out. So hence, if you have an aircraft with a nose wheel undercarriage, this aircraft would be horizontal, so that would balance out. But because this one's got a tail wheel, we've inclined the propeller from being horizontal to a slight incline. So by this blade coming down first, definitely more of an increase in angle of attack than this one going back up. Yeah. So distance travelled in unit time by the downgoing blade is greater than that on the upgoing blade, and therefore downgoing has a higher speed relative to airflow and for a given angle of attack. Therefore, it's going to produce more thrust. So we produce more thrust on one side, which will make the aircraft move in the opposite. So in this example, the propeller is turning anti-clockwise. If you're sat in the cockpit looking forward to the propeller, the left hand of the propeller disc produces greater thrust, and that will make it yaw to the right. Okay. So in other words, it's going to try and bring the back of the tailplane round to your left, which makes the aircraft yaw to the right. If we're getting thrust on one side, it's like having two brakes on your cars, having the brake on the right hand side but no brakes on the left. Braking right, you bring the aircraft round or your car round. Well, having more thrust on one side is going to try and pull the aircraft round. In other words, in this case, yaw to the right. Has everybody sort of following that so far? Any not quite got that? Let's see how we get on. I'll try my fantastic drawing skills on this board, which is not the best, obviously. Let's see. There's that. So if I was, let's draw a very, very basic cross. Very basic aircraft, okay? There's your propeller at the front. Oops. So what we're saying is, this will be your tail at the back here, okay? We have more thrust. I'll change the colour. I might just draw on this one. So we've got more thrust here, less thrust on this side. So by having more thrust on here, it's going to make it yaw to the right. In other words, it's going to move the tailplane this way, okay, which means we've got a new direction of the aircraft facing that direction. Does that make sense? This is going to try and get thrust. It's going to try and pull the aircraft in that direction. Okay, so we're yawing to the right-hand side because this propeller here has more angle of attack as it goes down the way than this one going up the way. Okay, so more power this side, more thrust. In other words, it's trying to pull the aircraft around to the right. So we're yawing to the right-hand side. And again, if we don't correct that using the rudder in the back here, okay, using the rudder at the back here, we'd have to counteract that. We'll keep turning round, and if you keep power on, you'll just do a big donut. Okay, so we don't want that. So that's effectively what's happening there. Everybody understand that one? Does that make sense there? Then my amazing drawing skills, I do apologise. Not the best. Okay. All right. Everybody happy with that? Not too bad? Good.
Once more, please.
Once more? You just want to see my bad drawing skills, don't you?
Yeah.
I shall try my best. We're just trying to kill time. One of the two. Right, let's see. I'll use the mouse instead. Seems to. Oh, don't want that. Get that. Let's get a pen again. So, let's see. Again, I'll draw two aircraft. I'll do it down here. So the first one, small aircraft. I hope you can see that on your screen. It's not the best size. And then I'll draw the other one, which will then be facing that direction. Okay. And we'll give it a little propeller at front. So there's your nice little propeller at front. And again, the propeller at front there. So what's happening is because you look at the angle of attack here, as this blade's coming down, purely because of the angle of the axis of the aircraft, because it's not straight, it's not horizontal. If that was horizontal, then this diagram would be equal. So the blades, as they rotate, would be in line like that. Okay, so we get even thrust on both sides of the aircraft. But because the propeller, due to the axis of the aircraft, is inclined, we get the propellers tilted. So because of the airfoil shape, remember the blade is asymmetrical, it's not symmetrical. In other words, we have got a blade, obviously exaggerated here, something like that, just like a wing. Okay, it's asymmetrical wing. I'm not going to try, I'll try and draw a symmetrical. Not the easiest way to do it. And there, that's probably as best I can get it. So if we put a chord line through there, okay, the chord line, this one is like there, but on a chord line on a symmetrical one is obviously it's the same above as it is below. Your profile for a propeller blade is asymmetrical. In other words, we've got a higher surface area on one side and the lower surface area another. Basically a wing, but we're rotating around, so it's asymmetrical. So remembering this asymmetrical type profile shape, not symmetrical. As this comes round, so let's the top one here, this point here, as it's rotating towards the screen, that'd be anti-clockwise, as it comes down here, as it gets to the bottom, the angle of attack from your rotation here is going to be quite large. So by the shape of the blade coming down, there's a lot of angle of attack, there's a lot of power, a lot of thrust. Okay, but as the blade goes back up the way, it becomes a negative angle in effect, almost. So the angle of attack from here to here now, although it's the same angle, but remember the blade has now changed round its position. Okay, not physically, but by rotating the other way, we're not getting the thrust, we're getting negative thrust. So we're always going to have, go back to your stand aircraft here, more thrust on this side, okay, which would be here as well, and we'll have less thrust on this side. And that's if this is a anti-clockwise rotation. In other words, this part here, the tip of the blade here, is coming towards the screen, okay? In other words, it's moving that direction, rotating that direction, yeah? So this propeller here is rotating that direction. So as it comes down, because of the angle of the aircraft, we're going to have more thrust. Well, if we've got more thrust here, it's going to try and go forward, isn't it? But it's only going forward on one side of the aircraft. So what will happen is there's nothing happening this side, so we actually get it trying to move it around that way. In other words, a yaw to the right. If you put your right rudder pedal down, your pedal would move the rudder to that position, which will spin the aircraft to the right. Okay, so by having more thrust this side, only half the aircraft's getting pulled. Well, in this case, it's the left-hand side of the aircraft's getting pulled, not the right-hand side. So we've got a drag on this side in effect, so it's going to pull it round to the right-hand side. And if you don't do anything about it on the ground, all you'll do, you'll just do a massive donut. You'll just go round and round and round. Okay, and that sometimes has happened in real life, where the throttle's stuck on the ground. They've not managed to catch it, and there's a video on YouTube somewhere where you see a guy chasing a plane on the ground, and he gets in the cockpit, actually jumped in the cockpit. Very brave man, managed to get control of the aircraft before, and all it was doing, the aircraft was on the ground, going round and round and round and round and round, because he jumped out of the aircraft to sort something on his own, left the engine running, the brakes were off, and he lost control of the aircraft. Very, very silly. Funny to watch, but not so much funny for him who's trying to catch the aircraft. But fair play, he got into the aircraft and managed to control it. Okay, so all we're saying here is the downgoing blade on an anti-clockwise rotation is going to provide more thrust on the left-hand side, which makes the aircraft turn, because you've got rear wheel steering, yeah, because of the tailplane here. It's going to spin it round, and you end up facing the right direction, okay? Because this part here is trying to pull the aircraft forward, but because there's nothing there, it's actually going to go round to the right, pull the nose round to the right. So in other words, make the aircraft yaw to the right. Okay. Again, I do apologise for my really bad drawings there. Oops, do that. Okay. Let's get rid of that nonsense. So let me have a little think about that one. And likewise, if that was a clockwise rotation, you would have more power this side, so it should make the aircraft rotate around to the left-hand side. It's because it's a tail wheel, a rear wheel tail on this one. Again, if the aircraft is horizontal and your nose wheel steering, which is more preferable, there'd be no angle of attack there or change in axis, so it wouldn't matter. These would balance out. Each downgoing blade would have the same as upgoing blade. Okay, it would balance itself out. It's only because the aircraft has got an incline, which changes the angle of attack from the downgoing blade. All right, that's all that's going in there. So I think what we'll do, I'll let you think about that one for a minute, and then we'll go for a quick break. Okay, there's quite a lot to take in there. Let you digest that one, get your head around it, and we'll check it after break. Okay, does that sound fair? Get a nice cup of tea or Gurkha beer, one of the two. Okay, right, guys, we'll see you back at past. All right, past. Okay, see you in a bit.
Okay.
once I get my pen to work. So what in fact happens there, that will turn the tail, push the tail over to the right, which moves the nose over to the left. Okay, so we're yawing to the left in this case, purely by the effect of the air spinning round the fuselage and hitting the fin. So what you can do, as I said before, you can alter the position of the fin, slight angle of incline in the opposite direction, which will counterbalance that as the aircraft's going forward, or maybe a little trim tab on the rudder as well. So when you do your hands off your stick, you're doing your trim checks. If the aircraft is tending to yaw to the left, we'll put a bit of right hand bias on there, and that will bring the nose back round to the right. Okay, and also affects how fast the engine's going as well. Now, propeller aircraft tend to go quite a steady RPM when they're cruising, so it will settle down. But just be aware, and likewise, if that was an anti-clockwise rotation, it would move the fin over to the left, which would make it yaw to the right. Okay, so that hopefully gives you a better inclination of what's going on there with the slipstream effect. Gyroscopic effect, well, think how a gyroscope works. We've got rigidity and precession. Excuse me. Now, as the tail wheel leaves the ground, you've got the torque applied to the rotating propeller in a nose down sense. The propeller's trying to pull that nose down, yeah? Now, the effect of that torque on the angular moment of the disc. So remember, if you had a spinning disc, that spinning disc is going to try and keep going forward. If we try and act perpendicular to the disc, we call it precession. We go back to your Module 2 physics days. So an effect of the torque on angular movement of the disc is like a precessing gyroscope. We're going to try and spin it. So in effect, what we're saying is the torque appears 90 degrees, removed from the point of application, in the direction of rotation, again producing a yaw to the right. Okay. I think I'm going to omit there. Anything else on that one? So again, think of the propeller as a disc, because if it's spinning fast, think of it as a solid disc. Obviously, it isn't a solid disc, but in relation to a gyroscope, we look at spinning discs, and a disc will try and go in one direction, but because of the torque, when our thrust is actually acting as the precession, then it's going to try and spin it in that position as well. So there's a gyroscope effect. So we've got, in this case, propeller spinning that way, more thrust on this side, indicating, now we can go back to the previous one where we had the inclination of the aircraft, and this gives you the same idea. Torque reaction increases rolling resistance, so slipstream effect, increase in fin, and the yaw will yaw the nose to the right. So we'll try and spin it to the right. So more thrust. This is trying to spin in one direction in that way, so it's going to try and rotate the aircraft around. So in other words, the tail will come over this way, and the nose will face over that way. Okay, purely by the gyroscopic effect. Okay. In conjunction with obviously the thrust as well. All right. Unfortunately, propeller engines, they're noisy. There's lots of vibration, especially piston engine ones. The gas turbines like turboprops, they're not quite as much vibration, but because the propeller and the air that causes turbines at the tips, we do get vibration. But piston engines, they definitely cause a lot of vibration. So in the cockpit, last thing you want to do is flying away and you're shaking away, and it's noisy, distracting, and obviously certain vibration can actually cause a lot of damage and fatigue to aircraft frames. So when a propeller is producing thrust, aerodynamic and mechanical forces are present, which will cause the blades to vibrate. Now, as you go through an RPM range of an engine, there's certain RPM ranges you're not supposed to stay in, because that's the frequency where that's the worst vibration is going to happen. Every single thing in the world has resonance. Okay. Now, speak of resonance, the mountains have resonance. Mount Everest has resonance. My cup of tea here has resonance. Everything has, even the table sitting on has resonance, albeit very, very little, but it is always there. In other words, we've got vibration. Every single thing in the world is vibrating. The molecules that build everything up are all moving. Some are extremely, extremely slow. Some are very, very fast. Like my cup of tea there, the water, the hot, the molecules are all moving about very fast, and that's what causes your heat. Now with propeller, we've got lots of moving parts, similar to molecules, but again, moving parts under certain conditions, that will cause vibration, and that's what we do not want in the cockpit. So vibration caused by propeller will cause resonance, which is produced by the echoing beat of an out of balance propeller. You might hear that on wind farms, get a thump, 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 thump. But some propellers, obviously, a lot more thumpier than other ones, depending on the size of them as well. So vibration usually caused by mechanical inputs, generally the cause of an out of balance blade or propeller assembly. You might have heard that in a car. You might have I've driven in Nepal, I know what the roads are like, very bumpy. Your wheels can get damaged very easily. So again, if you're riding along the road, you get the thump, 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 thump of the wheel, it's out of balance. So again, you have to rebalance it. Now, same for a propeller. If a propeller's out of balance, that's going to shake quite badly. And potentially, worst scenario, it could come off. And that's not a very good case to be in at all. Propellers, spinners, the nose cone and front propeller, and the powertrain dynamic components are manufactured to very, very strict tolerances. The slightest deviation from those can cause a major effect. And that goes for any engine, gas turbines, your car engines, your motorbike engines, and that sort of thing. Any slight imperfection in balance, it will throw things out. Now, due to central vehicle force, aerodynamic loading, individual component tolerances, and some residual out of balance moment might be present in the whole sim. There's lots of things going on that could put the whole thing out of balance. Okay, and that can lead to an increased balance, and once it gets so bad, it gets uncontrollable vibration, and we're at a point we can't control it anymore. The process of tracking and balancing propellers is generally required on the following occasions. So we're going to have to balance them and what we call tracking if they're in line. Exactly the same cars and wheels. So why might you do this? You might do it after a major component change. One, you've changed propeller. You've got a brand new propeller, you put a new propeller on, you might have to go and balance it. Okay. You might have changed the engine. Again, engine to propeller, you might have to do vibration checks as well. If for the fault, you're doing diagnostics. The pilot has reported vibration in the cockpit, and you'll go and try and figure out where the vibration is coming from, using test kit, using obviously visual indications, and basic diagnostic thoughts. All again, always follow your maintenance manual for procedures. And whenever required by the maintenance manual, or it tells you, you might have to go and do a vibration check every so many hours. Right, we'll go start the engine up, we'll go get the equipment on there, and we'll check what the vibration is. Is it in limit? Is it out of limits? If it's out of limits, let's go and see. Obviously, propellers are exposed to the elements. Again, there could be a little bit of damage on the propeller, or maybe it's had a little push or something. It's maybe slightly bent. Again, this is when we have to do these checks. Preventive maintenance is better than cure maintenance. So when looking at how to process of tracking and balancing compass, we have to determine what vibration is. Now, what is vibration? Rapid oscillation is caused by rotating assemblies when they're out of balance or by extreme influences such as aerodynamic losses. Oscillations were felt at certain force, and they are known as displacement or amplitude, and at a certain rate, in other words, frequency. Okay, displacement and amplitude. Vibrations per minute is known as frequency. We'll go and be back to module 2, your physics. Hopefully, this will you'll remember some of these terminologies. Okay. Just a recap on what we've got there. So we've got one cycle. I'm pointing the screen here. You can't see me pointing the screen. That's to the laser. So we'll start from there. We'll make a basic sine wave. At that point there, that is one period. Okay, that is one cycle. You'll get a maximum positive amplitude, and you'll get a maximum negative amplitude. Okay, and that's your amplitude is the normal part there, and then if you go from that peak to that peak, we call that peak to peak amplitude. Now, the closer that part is to that part, the more intense the frequency. So if I was to squash that wave closer together, that would be a higher intensity frequency, like be a higher noise vibration. Anybody here play a musical instrument like guitar or anything like that? Any guitar players here? Yeah.
James.
Yeah, exactly the same. You get different. I play guitar badly. I won't like endure my guitar capabilities. But every string, you pluck it, you're causing vibration. Now, depending on the thickness of the string, depends on the frequency, and how hard you pluck that string depends on the amplitude. Okay. So same for being out of balance. It's a rotating back and forward from peak to peak. Okay. and that will determine the amplitude. Now, the greater the amplitude, the more intense the frequency, the more intense the vibration. The higher the frequency, tends to be better than lower frequency, because if you've got a high amplitude and a low frequency, that's a big thump, 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 yeah? High frequency, very fine, sort of high pitch, high frequency. Now, resonance, you might have seen, say, you hear of singers, some opera singers with a high pitch ability in their voice. If they match the frequency, you've probably seen it in some films and on YouTube, if they match the frequency of a glass, they can actually shatter the glass. An amazing ability. So again, in an aircraft, if the frequency matches some other frequency that's within the aircraft, that can cause a lot of detrimental effect. And obviously, massive vibration, especially with turboprops and propeller engines. Worst scenario, your propeller is going to fall off or disintegrate the engine. So very, very essential that we maintain the propellers, maintain the engines, and make sure things are actually correctly tightened, torque set, and all the tolerances, etc. In other words, you're doing your job. You're following procedures. You're not just making them up on your own, and you're using the correct tools and correct equipment and correct part numbers and that sort of thing, and following as the manufacturers have determined that you should do. Things will break, damage will happen, and you're going to try and figure out what's causing the vibration. It could be something as simple as a loose bolt, yeah, just worked its way loose, or something snapped off. It could be an engine mount. It might not be the propeller. It could be an engine. Where the engine sits in the cradle, it could be something cracked. Yeah, again, that's down to diagnostics and following maintenance procedures. Okay, the vibration is generally expressed as frequency per second. Remember, that's in hertz, and 1 hertz is therefore equal to 1 cycle a second, and that's a movement from the baseline one direction and continuing in the opposite direction until eventually a baseline is received. Okay. So looking at that sort of thing there, we're looking like a little guitar string, so we'll bounce forward and backwards, okay, moving from the baseline, continue the opposite direction, and eventually it will return back to the baseline, okay. If not compensated for in design, vibration will cause, well, nothing good, unfortunately. Excessive flexing, hardening of metal, so if you've ever got a bit of metal and you bend it forward, backwards and forward, eventually heat up, and eventually what's going to happen, it will snap, yeah? So imagine a propeller blade going back and forward, back and forward, back and forward. Eventually, especially a metal one, that could work hard and snap, okay? So yeah, it results in section propeller blade breaking off during operation. Well, you certainly don't want your propeller breaking off during flight. That's going to make your eyes panic a little bit. I don't want that. Aerodynamic forces have a great vibration effect at the tip of a blade, with effects of transonic speeds cause buffeting and vibration, so that they're not quite speed of sound. They're transitioning from slow speeds up to sonic speeds or speed of sound. So as it goes through there, it rips through the air basically, and it causes a bit of buffeting and vibration. Okay, now the faster that's going, the greater the intensity of that is. We've got some big wind farms up here. You might have some in your area as well. Those big, massive blades up in the hills. As they spin round, you hear this thump, thump, thump as it gets close to the ground, because it's pushing that, compressing that air very close to the ground, and it causes a lot of vibration and buffeting. Vibrations may be decreased by use of correct aerofoil shape. Yes, so it's down to the designers to ensure we've got the most efficient aerodynamic type profile on the blade. And you'll see why the blade tips don't go straight, they actually taper off. That helps reduce buffeting as well. Mechanical vibrations also generated by power pulses in a piston engine, and they're considered to be more destructive in effect than aerodynamic vibration. So a piston engine with a propeller, very lots and lots of vibration. You've got the piston going up and down, so it's going bang, 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 like that. Lots of rotating components, heavy components, lots of bearings, lots of things that can vibrate. Whereas a turbojet engine with a propeller is far smoother. Less, yes, we've got the rotating shafts, the turbines and bearings in there, but there's not this bang, bang, bang going on. We've got a constant burn. The only things that are causing potential vibration is the propeller attached to it. As I said, the piston engine power pulses cause the propeller to vibrate and set up a standing wave pattern, which will cause fatigue and damage and potentially failure, which is not good. So location and number of stress points changes with different RPM settings. We call this a critical RPM range. So there's going to be certain RPM ranges where that propeller does not like to be in that range, and you'll have that on your gauges. Now, the most critical location for this stress concentration, and it's a good one to highlight, is about 6 inches in from the top or the tip of the blades. Okay, so you might want to highlight that in your books. So the most critical location, it's because it's slightly weaker. Remember, 2/3, 3/4 is the most efficient part of the blade, but the weaker part is towards the tip. So about 6 inches from the top of the blades. Most airframe engine propeller combinations have no problem eliminating the detrimental effects of these vibration stresses. The designers take this into account. So normally, provided everything's working okay, everything's all good to go. However, again, back to the old piston engines, combinations are sensitive to certain RPM ranges and have this critical range indicated in your tachometer, your RPM gauge, and uses a small red arc. Where you're allowed to go through that red arc, but don't stay in that position. There's always a certain point of vibration that it just doesn't like, especially in piston engines. And you can see here, you can see a little red arc here and a little red arc there. Yeah, green is good, as always, but red, not so good. So, okay, if you're transiting, you've got your RPM going up, the gauge is going up and up and up. Yes, you have to go through that, obviously, but do not sit in that range longer than is required to, because it's going to vibrate quite a lot. But once you get past that, the frequency catches up and it will cancel itself out and it'll be smooth again. Okay, so we have to watch out not to sit in those RPM ranges, especially in piston engine aircraft. So only transit through them where possible. So again, the engine should not be operated in the critical range unless necessary to pass through to a higher or lower RPM. Don't sit in that point at all. Every engine will be slightly different. The red arc will be slightly different position for each engine, but there's an optimal point where, yes, we don't like that point. If the engines operate in critical range, possibility of structural failure, again, not good. That's going to end in disaster. And the aircraft due to vibration stresses set up. Propellers, like I mentioned before, by a gas turbine or proper engine are not affected by that because there's a nice, smooth burn going on. And there are not power pulses in a gas turbine engine. There's not this banging of the piston going forward and backwards or up and down, depending on what type it is. We set the gas turbine on fire, the gas goes in, gas comes out, job done. Okay, that's module 15 done. Any questions on module 15? A little bit more than that next few weeks. As operation cycle is continuous, there is no intermittent or reciprocating action like in a piston engine for a gas turbine engine, and therefore far, far smoother operation. Things can go wrong with gas turbines. We can get damage to turbine blades, compressor blades, internal bearing damage just through debris and stuff. So yeah, we can get vibration eventually, but it tends to be a far, far less chance of vibration on a gas turbine engine, far smoother. So that means there's much less fatigue, operational stresses transmitted to the propeller, and the above mentioned technical data means that turboprop propeller should remain in service longer and more time between overhaul. Okay, time between overhaul, TBO there. Now, aircraft interior noise and vibration can be a very serious problem. And obviously, you're flying away. If you're holding a joystick and you're shaking, that's going to affect your body. You're going to vibrate and fatigue out. Vibration causes noise. Noises can often exceed 100 decibels. 100 decibels, that's quite loud. And if you're constantly hearing 100 decibels, that's going to make you go deaf, which is not good, and very distracting. You're trying to concentrate flying the aircraft, that's also very distracting and detrimental to you as well. Aircraft vibration limits can limit the fatigue endurance of the aircraft. Again, that will reduce the amount of hours that aircraft can fly, and also the comfort of the passengers. If your aircraft jumping over the place and the passengers in the seat and they're all bouncing about, well, it's not a very pleasant flight, isn't it? Again, can damage instruments and other bits and pieces. Low frequency cabin noise and vibration in prop aircraft, again, dominated by what's called the propeller blade pass frequency, or PBB, and it's low order harmonics. Now remember, a harmonic is just a continuation of the first harmonic. You get second harmonics, third harmonics, fourth, fifth, sixth. It's just a multiple of the very first one. Okay. Hence why, when we go back to physics, if I play badly the key of C on a guitar string, and somebody plays the key of C on a piano, well, it's the same note, but we can distinguish that that's a different instrument because of the different harmonic. It's the same note, just a different harmonic. Okay, that's what I mean by harmonics. Typical blade pass frequencies range from 60 to 120 hertz, and that's worth highlighting in your books as well, guys, just to make a note of that. So typical blade pass frequencies range from 60 to 120 hertz. Now, passive control of this noise and vibration is quite difficult, as you can imagine, and usually requires unacceptable weight penalties. We can put things into the aircraft to try and reduce the amount of noise and that sort of thing, vibration. But again, if we put more things into the aircraft to help this, that's increasing weight. We increase weight, we need more power. We need more power, we need a bigger engine. We need a bigger engine, we need more fuel. And what does it come down to? All the money, yeah? So we try to keep the cost down where possible. Now, many aircraft with two or more propellers have what's called propeller synchronization and synchro phasing. Okay, so two terminologies we'll come across and describe these a bit later in book 2. Okay, let's move on to there. But just for the moment, though, just be aware of the two types there. Okay. The signature amplitudes of propeller vibration have shown that outboard propellers contribute less to the cabin noise than that of inboard. Yeah, strange enough, the engines that are further out don't give as much noise as the ones that are closer to the fuselage. You've got the propeller blades coming into or very close to contact with the fuselage. You get the buffeting effect, the turbulence of air going around there as well. So also, one of the inboard propellers has more influence over the cabin noise than the other. They could have engines, both engines going the same way, but normally they contra-rotate, or one goes clockwise and one goes anti-clockwise, but most of them will go the same direction. So the blades coming down into the closer to the car, usually the left-hand one, will cause more vibration than the one going away from the fuselage. The axis of the propellers usually rotate in the same direction. The more highly loaded downgoing blade, as I said there, close to the fuselage, the corresponding will give the greatest resonance, the greatest amount of noise, the greatest amount of vibration and buffeting. So synchronization and synchro phasing, again, just take a note of these names for the moment. We're going to cover these in book 2. Okay, and we'll see how we can use both of those to get to a suitable point where we can reduce vibration and noise as well. Because you can imagine, basically, the background is that if you've got two propeller blade tips all hitting at the same time, they're going to increase the amplitude and potentially frequency of vibration. So if you put it out of sync a little bit, that can reduce it as well. And that's what we'll cover in book 2. All right. So what we've got at the moment, I think it's on page 78, unless we change the book numbers. You've got 9 questions there. Okay, 9 questions to go through. So if you want to have a little 5 minutes going through the questions, try and fill the answers in. We'll do 5 10 minutes. We can finish them all. Okay. We shall go through them again on Monday anyway. These are a bit of recap for you for your over the weekend. But certainly have these questions finished by Monday morning, because we'll go through them in the Monday morning. Just check your books. I know they've redone the books. Is it still page 78 the questions are on? Can somebody confirm that? Somebody just check your questions on page 78, please.
Yes, we do have question on page 78.
Yeah, that's good. Yeah, because I know they've not changed the book. They've updated the book slightly, but I've got more version, and there shouldn't be any difference in page numbers. So that was good. So yeah, take your time to go through these over the weekend or lunchtimes, whatever. And it's a good little bit of recap. We've got a few more questions coming up as we go through the book, and then on Tuesday we have lots of questions to recap. Okay. Any questions on vibration at all? Again, the synchronization, synchrophasing, we'll cover in book 2. So no worries there. So that's chapter 1 finished. That's pretty much chapter 1 finished. The only thing I'll go through now is you've got some terminologies, which I don't have on the screen, but instead on page 35, we've got some terminology we'll go through. I'll just go through them one at a time. So we've got accumulator. Again, you've done module living, stuff like that as well. So anybody tell me what an accumulator is? It's okay, nobody answers. Saroj, you tell me what an accumulator is?
Yes, sir.
What is an accumulator? We're just going through the glossy of terms. So, what is an accumulator? What does an accumulator do?
A device stored in a fuel pressure and used to add on phasing of propeller.
Yeah, good. Just a storage compartment. We can have some potential storage in there. Okay, for fluid, good. ATM, aerodynamic twisting moment. Somebody else? Thank you, Saraj.
Thank you, sir.
Harim, Hiram, what is the aerodynamic twisting moment, or commonly known as ATM? Okay, anybody else? Oh, he's back there. Harim, what was ATM, aerodynamic twisting moment?
Is a weak force.
Yeah, that's right. Yeah, purely by the fact it's a wing spinning round, it's trying to fly away, so it increases the blade down. Good. Okay,
Force speed.
Gajendra, what's angle of attack? Gajendra?
Yeah. It's chord line to the relative airflow.
Yeah, that's right. The chord line to the relative airflow. Good. I won't do them all because a few are quite straightforward. Okay. There we go. That's fine there. Just one or two I'm going to put through. What is effective pitch? What's effective pitch? Surab? What's effective pitch, Surab?
The distance move in one revolution.
Yeah, the theoretical distance. Yeah, so the tip blade, as it rotates forward in one direction, it should be that distance. The example showed you was 50 inches. So when the propeller rotates one full cycle, it should move the aircraft forward. In that example, was 50 inches. However, it never happens because it's never 100% efficient. We have that little bit of slippage in between there. Good.
Yeah.
Okay. The pressure face of a propeller blade, would that be in the front of the propeller blade or at the back of the propeller blade? How about Sundeep? The pressure face of propeller blade, is that on the front of the propeller blade or is that on the back of the propeller blade? Yeah, it's basically, if it was a wing, it'd be underneath, yeah? If it was a wing flies through the air, that's where your pressure face is. But a propeller is obviously spinning through, rotating through the axis of the engine, so it's the bit behind it. That's where the thrust is done. Good. Okay, that's fine. Just a few questions there, but those questions on page 78, again, just go through them in your own time. You can do them over the weekend. It's good revision. And I say, hopefully Sanjeev will have printed out or given you the questions I've got for you as well. And they've got the answers there as well. But yeah, go through the questions. Good for revision. Okay. See.
The strongest force in propeller is what? Centrifugal or torsion?
Right, so
Centrifugal.
I'll just change that now. 2 seconds, guys. Just bear with me.
CTM.
CTM, yeah. Centrifugal twisting moment. Strongest force, right? Strongest CTM most powerful भयो अनि सेन्ट्रिफ्युगल चाहिँ लार्जेस्ट फोर्स हो के के खैरे टोलाएर बस्यो त
Very good. It remains like that.
your mic off.
So yeah, I was just changing that slide. Yeah, you can do a couple of questions at the moment, but you can do some of them. You can finish those off at the weekend. We'll just move on. We're going to try and finish book 1 by, well, we've got chapter 2 to go now, and there's not many left in chapter 2. It's quite straightforward, thank goodness, so not too bad at all. Again, some questions of chapter 2, so we've got about 80, yeah, about 30 pages or so. So we'll finish that probably about by lunchtime, and we'll start on book 2, okay? Yeah, right, let's move on a little bit. Again, those questions you can finish off in your own time. I've got some more questions come up again, but we'll just move on with chapter 2. So it gives more time for revision by Tuesday. Okay, chapter 2. We're going to look at propeller construction now, how you actually make the propeller, that sort of thing. So, propeller blades are made of wood, steel alloys, forged solid aluminium alloys, and composites. Okay, again, worth highlighting those ones because they might ask you a question, what's the propeller blade made of? So we've got 4 options there. The hub where the propeller sits into are usually made of cast steel or aluminium alloys. Again, so it's worth highlighting those. Just wet my whistle. So wooden blades. First wooden blades, you can imagine, very, very crude, very, very basic design. Not very reliable, to be honest. Made of a solid block wood or possibly laminated once they got a bit newer. And now, these ones definitely highlight, please. The common types of wood used for propeller blades are mahogany, cherry, and black walnut, and also oak. Very hard, tight woods, yeah? So mahogany, cherry, black walnut, and oak. So worth, again, highlighting those ones. And the last one is birch. Now that's the most common type of wood they're going to use. So a question could be, what's the most common type of wood used to make a propeller? And your answer would be birch. Okay, but you've got 5 types of woods there, and birch being the most common. So yeah, you can highlight those. So looking at a blade, okay, there's various types of designs, weird and wonderful, for some very wonderful ones like that. Usually the laminated ones are made of layers and layers of wood to make it stronger and more durable. But the basic one, you will have a laminated type wood blade. You might have some fabric, sort of sheen as protection, and you might have some metal protection there. Again, we'll look at that in there. Again, just helps protect the edge of the blades from potential damage. All in the middle, you have some sort of hub assembly to actually bolt onto the flange of the engine. But they all start off as a basic laminate type supply. But you can see here some very basic and some very weird and wonderful designs to some very, very, very basic ones there as well. All doing the same job. So there was a close up the same thing, yeah. But most propellers nowadays are made up not just from one solid block, because that's too weak, actually made up of laminates compressed and glued together, shaped into profile, and such. So we'll look at what's called the 3 stages of wood propeller production. Now, going back to that diagram there, you have all these planks which will be glued together in a set format. Then we'll do what's called a white process, and that's the initial shaping. And then the finished one is the final profile shape. So there's 3 procedures. We glue them all together, we compress them together, let them dry. We then get a very crude shape, which is called the white process, and then the finished propeller is, as it sounds, the finished one. So each layer of propeller is usually the same thickness and type of wood. There's no point in putting different wood in there because it might have weak properties and that sort of thing. So by using the same type of wood, making a laminate makes a nice, light, but very solid process. One to highlight here is there must be a minimum of 5 layers of wood are used. The planks of wood are glued together to form what's called a blank. In other words, just like that previous diagram, 5 layers of wood glued together, that just makes initial blank format for the propeller. And then good to highlight there. During fabrication of blank, it's roughed to shape and it's allowed to set for a week, so 1 full week, to allow equal distribution of moisture. Yeah, the glue glues it together, but we need to let it dry out and evenly dry out through all 5 layers. So we'll leave it for 1 week. And then the rough shaped blank is called a white. All right. So that's once it's all dried out, you've got this very crude looking propeller, and that's once it's all glued together, all dried out, we call that a white. And then that white will be then finished to your exact aerofoil as is required by the company. So 5 layers, glue it together, leave it for a week. Once it's a week, that's called the white, and then we finish that off. So that's your 3 parts. So there's your white getting profiled, getting into shape. So you'll see that all the layers will have been laminated together. That's been glued for a week. And then I'm start cutting it on. Obviously in the old days, it was all hand done. The skill back in those days must have been unbelievable. Hand carved propellers. Nowadays, all done by machine, with a little bit of hand procedure going in as well. So very, very clever people back in the day. Other types, we've got this construction of Rotol or Jable wood type blade, and it's just another version of a lamination. And some have got covers and screws going in there. Again, if you start putting screws and stuff, you start to weaken it and that sort of thing. This is that old type of what's called a Jablo wood blade. All right, just a different version. So wood blade protection, can be protected by use of steel, fabric, or plastic strips along the leading edge and also the tips. Just in case the aircraft may have a heavy landing, it could potentially bounce. And I should have taken a photograph in the hand. We've got a nice propeller. As the aircraft landed, all 3 propellers were bent back the way. I should get a photograph of that sometime. Wooden blades are usually varnished or painted for protection to help them against the atmospheric conditions and the climate conditions. Tip fabric is usually applied to the propeller as well. It just helps strengthen bonding and protection as well. Now, the cotton tip fabric that is used is glued to at least 12 to 15 inches of the propeller blade and it helps to reinforce and strengthen the thin section of the tip. So yeah, as the propeller gets thinner towards the tip, this fabric on there just helps to reinforce it. By having a smaller tip angle and a smaller cord, it reduces weight, reduces stress, but by reducing stress, we can unfortunately make it weaker. So by putting this fabric around it, that can help strengthen it at the same time. Now the fabric is doped. The doping is just a procedure where it's gone and dry, and it's put with special glue and stretched over and allowed to dry. Now in the old days, wings were covered in a fabric and put with this type of varnish that would, or gluey varnish type substance, and we call it doping. So you put it on, and as it dries, it shrinks into position once it dries. So when it goes on wet, put it in position. As it dries, it contracts and shrinks to make a nice rigid surface. And that's how a lot of the old wings, and certainly World War II, Spitfires, Hurricanes, some of the skin wasn't metal around the aircraft. It was actually this dope material. Propellers then varnished with a coat of water repellent clear varnish, and that helps protect the surface. Again, you might see some propellers are painted just for decorative purposes. And also at night time, you know, we might have fluorescent type paint on there. You can hear the propeller, but at night time it's very hard to see it. So sometimes the paint actually helps as a visual aid to let you see where the propeller is, especially if you're in close proximity, which you shouldn't be. So types of protection might come across. The sort of notch type is these little plates, make it look like a set of teeth. Okay, by doing that, it helps reduce a little bit of weight, still reinforces it. We've got solder joints, and we've also got a drain hose, because where these metal plates are put over the wood and then screwed in position, well, there's potential for moisture to get underneath there. And if the moisture gets trapped at the very leading edge, we can escape it through drain holes. Or by the plain tipping one, just a band of metal going over the tip and the blade, so far better than that. Slightly heavier, possibly. Okay, so we call this one the scallop tipping, and we call the plain one, strange enough, the plain tipping. Okay, attached by rivets or screws. So again, if there's a hole in the screw or a rivet, there's potential for moisture to get in there. Hence why we have a drain hole, to allow the moisture to drain away. Some propellers do not use tip fabric, but are coated in plastic, and before the metal tipping is actually applied. That helps prevent corrosion and damage to the actual wood, and because of metal and wood, again, that can cause effects as well. Plastic coating provides protection and also adds as strengthening aid at the same time. Now, wooden blades for constant speed propellers. So wooden blades for controllable pitch propellers are constructed in the same manner and fixed pitch propellers, except that the blade is placed in what's called a metal sleeve at the root and secured with lag screws. Okay, so there's your whole metal propeller. There's your protection capping, some fabric sheathing there to strengthen it, and then the wood part will be fitted into this metal sleeve. So it'll be designed to fit in there and secured in there. Okay, so that's a wooden blade constant speed propeller. That way, this little spigot here, you can actually adjust the pitch of the blade. Steel blades, more common nowadays. Forged steel or steel alloy blades. Again, steel propellers are found primarily on vintage and even older ones. Steel, well, steel's going to rust, so we tend to use the aluminium alloy ones these days, but certainly the older ones are steel, far better than wood, but can fatigue as well. Normally a hollow construction helps make them lighter, so you've got lightness and strength at the same time. Prime advantage of hollow blades, again, obviously reduced weight, reduced turning momentum, and forces acting on the blade. Now, steel blades with a hollow sole are very durable and resistant to damage. Again, steel blades will corrode through time if they're not protected. Aluminium blades, your forged solid aluminium alloy blades, most widely used ones nowadays in propeller aviation. Easy to manufacture and easy to repair, potentially as well, and a lot cheaper compared to steel. More desirable than wood because they're thinner, more efficient airfoils, and used without sacrificing structural strength. Also provide better engine cooling by carrying airfoil sections closer to the hub and directing more air over the engine. So as well as being lightweight, strong, effective, they help with cooling the engine at the same time. Always quite good. Propellers require much less maintenance. You still have to inspect them, obviously. They are prone to damage than wooden ones. The wooden ones obviously are more susceptible to damage. Therefore, less maintenance means less time on them, which means less money. And all unfortunately comes down to the money, doesn't it? The forged solid aluminium alloy blades, made from aluminium alloys, finished to whichever shape is required for that aircraft by machine milling, manual grinding, and a good final polish. The polishing get nice and smooth, so there's no roughness on it, just like a wing and like a fuselage. Pitch is set by twisting the blades to desired angle. Again, nowadays that'll be done in a special machine, not so much on hand twisting. However, some of the early ones were done by hand. As propeller's been finished by grinding, its balance is checked. We need to know the balance, and adjusting by removing metal from the tip of the blade to adjust for what we call horizontal balance. So remove it from the tip, and then from the leading and trailing edges of the blades to adjust the vertical balance. And we'll look at this in a little bit more in depth. So these are worth highlighting. So if you want to check the horizontal balance, it's from the tip. If you want to check the vertical balance, it's from the leading and trailing edges. Again, potential questions from either or of those ones, so worth highlighting there, guys. Some fixed pitch propellers have horizontal balance adjusted by what we put actually lead wool in the balance holes near the hub, and the vertical balance corrected by attaching weights to the side of the hub. Okay, so we can actually put steel wool in the holes near the hub, or for the vertical balance, instead of removing material, obviously, we can add or reduce weights as appropriate. Again, very similar to a car wheel, where you get a wheel balance, you'll add weights to outside the wheel, But in a propeller, we can actually put it in the hub or outside. Now, one is for horizontal and one is for the vertical balance. Once the propeller is ground to design contours, the profile, the balance is adjusted, the surfaces are finished by plating, either by chemical etching and possibly painting as well. Okay. Anodizing is the most commonly used finishing process. Now, anodizing, you can do any sort of colour as well, but anodizing, the chemical process, electroplating, etc. So there's your basic propeller before it gets finished. It'll be cast and then finish off to whichever desired shape is required. Composite blade construction. A third type of construction incorporates composite materials. And one example has a solid aluminium spar and it has a polyurethane foam filling. The foam filling fills up the gap, but also helps with rigidity as well. Reinforced resin airfoil shell covered with a tough polyurethane coating for erosion protection. For protection provided by a replaceable erosion fibre, near the blade root, and nickel sheaths again, just like we saw in the wooden ones, on the outer and leading. It helps to protect it. Although carbon fibre is very strong, it can shatter. So a little bit of protection, you can put the nickel sheaths. Features are built in, such as braided type lightning conductors and electrical de-icing elements, which can either be replaceable or built in into the construction. Now, a typical composite blade construction can consist of a solid spar, alloy spar, around which you have a fiberglass shell with the correct airfoil shape in place. Again, all specific to the design of the aircraft and the engine. Now, the space between the spar and the shell, again, is filled with the plastic foam, and that provides support. Without that support in there, it could collapse. So by putting a very simple foam in there, it expands out and it stops it compressing. And also it's lightweight as well. So there you go. There's your main support, your aluminium spar going through the middle for the main rigidity. Then you have your foam in these outer inner holes, so it helps take out the gap. The fiberglass shell all around the outside. Okay, so a very light but very strong type setup there. That's a basic composite blade construction. Another type. Now we'll go back to that one. So we call it a monocoque type construction because you've got a strengthening point here, strengthening point there because of the spar, then a space. Then by purely the fact that they've got a shell around there, we call it a monocoque. It's not a solid construction, a monocoque construction. Or semi-monocoque. Now, another type of semi-monocoque is the Kevlar. You probably had Kevlar for like bulletproof and stuff like that as well. A lot of gets you military type scenarios. Very strong, very lightweight, very durable. A lot better than carbon fibre. Consists of a unidirectional and multi-directional layers. So you've got one layer like that, and then you have another layer like that going across them, so they interweave with each other. Again, bonded by some sort of glue or epoxy, and that will form a shell laminate. So there's your semi-monocoque construction. Yeah. There's your foam inside again. Your laminated Kevlar, which forms the basic framework of it. And by having these struts in here, that maintains the rigidity of the airfoil. So we've got lots of space in there. But again, you have a solid Kevlar at the leading edge and at the tip, just for a bit of strength. We don't need it in here. We can use the lightweight foam. That takes up the gaps, which is all nice and good. Leading trailing edge, again, usually reinforced with solid unidirectional Kevlar. So a lot stronger, a lot lighter, a lot more durable. And just for mention there, these ones here are called shear webs, little supports. Okay. Now, two unidirectional Kevlar shear webs are normally placed between the camber and the face, which is supposed to the shell to provide resistance to stop them flexing and bending about and that sort of thing. Again, the polyurethane foam fills the space inside the shell to support the actual blade and resistance, any distortion which could cause operating stresses on the propeller itself. And that's a cross section of it. You see the polyurethane foam core, you see the carbon fibre spar around outside here, again filled in there. Polyurethane coating outside, nickel strip again, just for a bit of durability, and also a lightning conductor built in there, which will be off to Earth somewhere. Carbon fibre, as it's flying through the air, can cause static. So, like any aircraft, aircraft is designed to take lightning strikes, and so if a lightning strike hits a propeller blade, it will go through the lightning conductor, which will air through the engine and air through the frame, and out, hopefully through the wingtips as normal. If it didn't have that there, if a lightning strike hit the carbon fibre, it would just explode and you'd lose the propeller, which is not so good. Okay, so these lightning conductors are braid-type lightning conductors and electrical de-icing elements. We can put power through there, which can be either replaceable or built into the construction. If they're built in and they're damaged, you're going to have to replace the blade. So it depends on the type you've got. Repairs, there is very little or no repairs allowed in these times. Carried by operators on composite propellers due to tech required. So again, it's going to be replaced by manufacturer. So any repairs should be carried out strict adherence of a approved repair schedule, as long as you're authorised for that. If you're not authorised for it, you can't do it. Okay. But usually damaged propeller blades are returned to the manufacturers, especially carbon fibre ones. Okay, and composite ones, they'll go back to manufacturer. Some of the carbon ones, you can do minor repairs. If it's a serious repair, it goes back to manufacturer. Examples of carbon fibre propellers, diagrams there. Usually by sort of black coating, you can see there. Very strong, and you can see that there's the grains of the carbon fibre, okay? Interweaving cross-member type bits and pieces. Again, helicopters these days as well use them as well. Very strong and robust. Okay, right, let's see where we're at. Okay, how far we've got left. Cool. Okay. Right, we'll just finish off for a sort of a quick 10-15 minute break there, and then what we'll do before lunch, we'll do a bit of recap. Okay, I don't want to move on to the next bit until after lunch. Let's move on to propeller types. So that's 9:30 now. If you come back about 1:45, 10:45, we'll have a little break there, and we'll do a few questions just before lunch, and then we'll come back after lunch. Okay, any questions on those parts at the moment, on which the blade angles cannot be altered without bending or actually reworking the blade? So these type of propellers are suitable for certain aircraft to do a certain job, usually the smaller type of aircraft. Now with a fixed pitch propeller, an increase in engine power causes an increase in rotational speed, and this causes more thrust. Yeah, makes sense. Now this in turn also creates more drag. Like we get nothing for nothing. So yes, we get more thrust, fantastic. But remember the four forces acting in the aircraft: the thrust, lift, weight, and drag. And then propeller, thrust and drag. Drag is always fighting against thrust. Yeah, more thrust means we induce more drag, unfortunately. And the force in propeller to absorb the additional extra power. So in a similar manner, a decrease in engine power will therefore cause a decrease in rotational speed, and therefore a decrease in thrust. That makes sense, doesn't it? We decrease the power, we're going to lose thrust, and we'll lose rotational speed. When aircraft with a fixed propeller drives the forward speed of the aircraft, the forward speed will increase. And since there's a change in the relative airflow, there is a reduction in both thrust and drag with a corresponding increase in rotational speed. The opposite effect occurs during a climb. In other words, an increased angle of attack. So we'll go back to, we saw this morning about the aircraft on the ground and increased angle of attack. An increase in thrust, a decrease in rotational speed. Yeah, we get more power, but we get a decrease in rotational speed at the increasing angle of attack. And a climb, sorry. Propeller can only absorb a limited amount of excess power by change of rotational speed, because beyond these limits, damage to the engine will occur. It's putting too much stress on the engine. We're getting the thrust, fair enough, but that's reducing, it's trying to twist itself off the crankshaft of the engine, so that can strain the engine. So only for a limited amount of time. That's like you driving your car, you got your forward speed, you're going up a hill, you're in 5th gear, and if you don't change gear, you can keep the throttle on, but that's putting a lot of stress on the engine, a lot of stress in the gearbox, and eventually you probably conk out or damage your engine. Same for an aircraft. Now that's led to the development of what we call controllable pitch propellers. So we actually change the angle of attack of the propeller itself. Rather than a fixed pitch one, we can actually change them as required. Again, manually controlled or automatically controlled. And we'll look at these in part 2. So, disadvantages of a fixed pitch propeller. A fixed blade angle will only be efficient at one combination of airspeed and RPM. It all depends on the angle of attack of that propeller. If it's going for a long cruise one, like the examples I mentioned before, like the Red Bull Racing, very quick turny aircraft. Okay, they're not for mega high speeds, but they're very torquey, very powerful. Okay, or it's just a normal cruise one. So it all depends on what's designed for. So during takeoff, the angle of attack will be large because the airspeed is low with a high RPM. Until the aircraft forward speed catches up, then it will decrease the angle of attack. Again, depending on the size of it. So a fixed pitch propeller with a high angle of attack is going to take a lot longer to get the speed for the aircraft before it gets the torque going. Okay. Hence why when we use movable propellers, we can put a low angle of attack to get the torque to get up quicker. So a high angle of attack fixed pitch propeller will generally take longer to take off than it would do with a variable propeller until it catches the forward speed. With the blades nearly stalled, acceleration is poor and a longer takeoff run is required, just as said there. Okay, does that make sense? Yeah, you've got quite a high angle of attack, so as it starts up, until the aircraft starts going forward to get a lower angle of attack, which gives more torque, will take generally a longer runway. Now, these fixed pitch propellers come in various shapes, sizes, and angle of attacks, so you can actually, for the same aircraft, if you want to have a bit of a play, get up very quickly and just throw the aircraft about for a bit of a fun on a Sunday, you probably put a small angle of attack propeller blade on. If you just want to go for a cruise, as in take off and go for a longer distance, you put a higher angle of attack blade on, and then, yeah, okay, you need a longer runway, but you'll be able to cruise maybe longer distances as well. Okay, so you can unbolt them and bolt them on as required. But again, that's a bit of a pain because you take the propeller off, put it on, and check it, and all that sort of stuff. But it is doable. Excuse me. So there you go. Disadvantage of propeller: aircraft speed low, large angle of attack. But once it gets to cruise, you've got the forward momentum of the aircraft, so therefore your angle of attack is less, so you've got more torque available, more power available. Okay. So until it gets to cruise, it's not really doing as efficient as it can be. Cruise conditions: angle of attack is small, and forward speed is limited to prevent an engine with speed, because if you get the forward speed too much, then the angle of attack got really, really small, which will allow the propeller to go faster because it's cutting through the air sideways a lot quicker, which potentially could overspeed the engine. So we do have limitations on forward speed of the aircraft. And the fixed pitch propeller has to compromise to improve takeoff performance by reducing cruise performance. So again, it comes down to design what you want that aircraft to do, and again, designers will accommodate that. So the accommodator comprised of cruise and takeoff. We need a variable pitch propeller is used instead, so it gives us the best of both worlds. Okay. So there's a fixed pitch little diagram here. We've got propeller efficiency. Remember, it gets about 80–85% maximum. So a fixed pitch propeller, okay, with relative forward speed. So not very fast there, but you know the forward speed is about 80% efficient. And any faster than a fixed pitch, then the efficiency drops off. A variable pitch one is almost like a gas turbine engine, very, very linear, up till a certain aircraft speed where it can't go any faster, and then efficiency will drop off rather rapidly. Now, what you can see here is the variable pitch one, if I put a line across there, tends to be a lot less efficient overall compared to a fixed one. Fixed one's very, yep, good, bang, I can do that. Variable one is more consistent, but not quite as efficient over a longer range, but certainly far better for forward speed. Okay, it can go far variable speeds compared to your fixed pitch. Fixed pitch is very short, it can't really cope with that. So a variable pitch propeller maintains efficiency pretty much over a wider range, where a fixed pitch is just a very limited range, unless you physically take the propeller off and put a different angle of attack on. Okay, so it just shows you a slight difference between the two. So we've got what's called ground adjustable propellers. Now, ground adjustable propeller is designed to permit change in the blade angle when the aircraft is on the ground. So you can see here, now these are manually changed one. You can see in the photograph, we've got 0 degrees up to about 40 degrees angle of attack. Or blade angle, sorry, not angle of attack, blade angle. Okay, so we can actually unbolt it, move the positions manually, rebolt it in, and make sure you do the opposite side, obviously. And that can change it, that allows you to change the angle of attack without physically taking the propeller off. Like the old ones would just be bolt on, bolt off. These ones you can actually change to suit the conditions for the flying that day. So it permits the adjustment of propeller for the most effective operation under different conditions of flight. Again, it was a really, really hot day, lack of air, low density air in the vicinity. You might want a smaller blade angle to get the more torque. A nice cold, thick day air, you can go for a coarser one. You can take off a lot better. And you can just see sort of mechanisms there. So as you adjust one, these mechanisms will be interlocked. So as you adjust one blade, it will adjust the other blades as well. Okay. Again, this is a manually changed one. Ground adjustable. Again, people like yourself, engineers, will adjust them, and the pilots. You know, if they're private pilots, they can adjust them as well. So if desired the aircraft has a maximum rate of climb, the propeller blades should be set at a very low blade angle. Yeah, you want it spinning nice and fast, give you as much torque as possible, so you'll be able to take off quicker. So it gives you maximum power available. So you want a high rate of climb, so you want all the power available. So a very small angle of attack, or blade angle. And we can check out using protractor as well. The blade in any case must not be set at an angle which will permit an engine to overspeed. So yes, we can change the angle of attack to quite a small one. Or blade angle, I keep saying, sorry. But if we make it too small, yeah, there'll be lots and lots of torque there. But again, you be careful it doesn't over torque the engine, overspeed the engine. So when you get the desired angle, an engine operate efficiently at cruising speed and high altitudes, the blade angle will then be increased. We'll make it a coarser blade angle. Okay. So if you want just a cruisability, we'll make a larger blade angle. Now, the ground adjustable ones, they might have blades made of wood or metal, or combination sort of thing. Yeah. Basically clamps. So there's a nice little twin one. Two propellers. You've got a clamp on that side, a clamp on the other side, and most of the time they'll be interconnected. So if you just slacking off the clamps, you move one propeller blade, the other one should move as well. Okay. I think the old type is individual, which could lead to problems. So the hub is usually a two-piece steel construction with clamps or a large nut to hold the blades securely in position. So when desired blade angle is required, the clamps and blade nuts are loosened. Okay, blade is rotated, get the angle you want for that day, and indicate by using the protractor, which we saw earlier on. Okay, so you physically twist the blade backwards or forwards. You'll have a protractor, and the little needle there will move forward or backwards to the relative angle that you want to set for. So again, the greater the angle, the coarser the blade, which means you need a longer runway. The shorter the angle, the closer the angle, the quicker you can take off. Right. It all depends on the conditions you want to fly in. Now, constant speed propellers, the type of propeller control what's called a speed governor. The governor is in charge. That controls what's going to happen to the speed of that propeller. It automatically adjusts propeller pitch to maintain the selected engine speed. So no matter what the pilot's doing, he wants a lot of power, not a lot of power. The constant speed one will rotate the blades automatically to maintain the speed. So the propeller isn't overspeeding or the propeller isn't underspeeding. It will sense that pressure in the system. And we'll describe these more in detail with book 2. Okay, so the constant speed, we don't physically move it, it's down to the speed governor. So if the RPM of the propeller tends to increase, in other words, the engine's getting too fast, the governor senses the increase in pressure and it will cause the propeller blade to increase. In other words, it'll put more load on the engine. So if the propeller's going too fast, in other words, it's cutting through the air sideways too quick, by coursing the blade off, make it a larger angle of attack, that puts more load on the propeller, which will help slow it down. Okay. When the propeller tends to decrease, or the RPM drops, okay, so it's getting too slow, the governor will sense a decrease in propeller blade angle, and cause a decrease in blade angle, which allow it to speed back up. It can cut through the air easier. An increased blade angle will obviously decrease RPM, and a decreased blade angle will cause an increase in engine RPM. Okay. Less load or more load. So constant speed. So we've got forward speed. There's RPM there. Small angle of attack because the forward speed that will sense that. High RPM. Forward speed is low. Again, angle of attack is low as well. RPM set by the pilot, but the angle of attack remains at optimum under all conditions. So it saves the pilot having to go and adjust propellers before flight. The governor will make sure that depending what the pilot has set the RPM to, it will compensate and move the angle of the blade to compensate for that. So it's not too fast, not too slow, but matches the RPM speed under all conditions. Okay, so just another diagram there. Angle of attack, RPM low, forward speed again, and such like. Cruise or high altitude as well. Now the pitch change devices for constant speed propellers include, now you might have electric motors, to obviously move them, hydraulic cylinders, rings in there as well, a centrifugal force on counterweights, or a combination of all the above methods. So a few different devices can actually move these blades for you. Now, what we call a PCU, a propeller control unit, does what it says, or a constant speed unit. They're both pretty much the same thing. These are the governors which will change and maintain the selected angle for the blade. So a PCU or a CSU, propeller control unit or a constant speed unit. And we'll see where these are used in. In this condition, optimum angle of attack, the propeller blades will be selected at all times. Blade angles can be changed as much as 110 degrees, which allows the propeller to be feathered. Remember, feather was in line with the airflow. And also used as a power brake, so we can put it into a very fine position. So it acts as a wind brake. And again, reverse pitch for reverse thrust, thrust reverse as well. Now, the PCU or CSU, they work exactly the same, pretty much, bar a little bit difference, but they look the same. Top of the gearbox, you have a PCU, tend to be for a turboprop engine. So PCU for turboprop, P for prop, remember it that way. And you got CSU is for your piston engines. Again, pretty much do the same thing, but just a slightly different terminology. So constant speed drive unit or the PCU version, propeller control unit. So CSU for pistons, PCU for turboprops. Remember, turboprop is a gas turbine engine with a propeller on the front of it. Okay, worth highlighting those ones. There we go, that's what it looks like. There's your propeller at the front. Okay, attached by whichever means to your reduction gearbox. And your little governor friend there is sitting on top. Again, PCU or the CSU. So again, PCU for your gas turbine, turboprop, and CSU for your piston. But they'll pretty much look the same, give or take a slight variation. And all that's doing is sensing the pressure or the speed from the engine or the speed of the propeller, and it will adjust using whichever mechanism has been fitted at that time. So inside there, you've got springs, you've got shafts, you've got sensor pressures, you've got lots of things going on. Okay, oh, somebody's beep there. There we go. Mr. Kumar. Right, so that's what it looks like inside, and we're going to look at that a bit more in depth and how it operates. You can see some spur gears there. So again, there's a drive shaft, so it's attached to the gearbox is spinning it. Okay, so we've got the drives going there. Again, you have the fluid in there, we have valves moving up and down, and that's what we're going to do. We've got flyweights, lots of things going on inside this little, very small component, relatively small, and all it's doing is sensing the pressure, sensing speed, accordingly. Okay. All right, here's that, come back in. Okay. Now, an engine and propeller combinations. Now, propeller can be at the front of the aircraft, the propeller can be at the back of the aircraft, or the propeller can be at the front of the engine, and the propeller can also be at the back of the engine. So I've got a few terminologies here. So an engine that's got a class as a puller, we call a tractor. A tractor pulls things. So this is when the propeller is fitted to the front of the engine, and the engine is then normally located in the front of the wing. So it's pulling the aircraft. Hence, what's a puller, like a tractor in the field. The tractor's pulling things behind it. A tractor type engine is pulling the aircraft forward. Thrust will be just forward as well. And engine propeller combination again says it's normally known as a puller or a tractor in that type of combination. More conventional combination of engine. Pretty much what you would normally see. A pusher, as it sounds. Okay, an aircraft with a pusher configuration has the engine or engines mounted at the rear forward of the propeller. All right, giving appearance that the aircraft is actually being pushed from behind, pushed through the air. And sometimes the propeller is situated at the rear of the fuselage, more commonly mounted behind the crew compartment, with one or two booms supporting at the tail. And we'll show you some examples in a minute. Each propeller can be also mounted on the wing, in which case typically located behind the trailing edge rather than on the leading edge of the wing. So the same sort of thing, but the engine at the back, the trailing edge, and it gives the effect that's pushing the aircraft through the air. In a push configuration, airframe is propelled by a force applied in compression from the rear rather than tension from the front. There's a little diagram, so a pusher and a puller. Okay, so you've got direction of the aircraft at the front. There's your typical sort of scenario: engine in the front, propeller in the front. So that's your puller or your tractor. Where if you put the engine in the back and also the propeller at the back of the engine, so on the rear of the shaft, that is classed as a pusher. So that's pushing the aircraft forward, where this one is pulling the aircraft forward. So that's your puller stroke tractor or pusher. Okay. Different configurations. Why do they do that? Because they can. It's down to designers. You'll see some weird and wonderful configurations. Why do it? It's because they can. That's it. It depends what the aircraft's designed for, but you do see some weird and wonderful configurations going on. Now, there's positives and negatives about each type, and that's what we're going to discuss just shortly. So, advantage of a pusher. Efficiency, it re-energizes the boundary layer air and reduces form drag. So the boundary layer over the wing gets used by the engine and the propeller, and it helps reduce the form drag. Bit more manoeuvrable because the rear thrust is less stable. Better visibility for the pilot, yes, and instead of having big propellers out the left and right hand side of your screen, they're at behind, so you actually get better visibility, which is always a good thing. Improved pitch and yaw, single engine placed closer to control surfaces, yeah, improved pitch and yaw. Safer, engine is behind the crew and passengers. So yeah, if something goes wrong, it flies off, doesn't hit the passengers and crew. A bit quieter as well, because engine's rearwards, yeah, it should be a little bit quieter. Less chance of a flat spin due to forward mounting, okay, for a puller. So a tractor, because it's forward, if you've got somebody pushing you from behind, that's equivalent of a rear-wheel drive car or a front-wheel drive car. If you lose control in a rear-wheel drive car, like a BMW, you can end up doing circles and circles and donuts, as we call it. Whereas you've got a front-wheel drive car, you might squiggle a little bit, but usually a bit more controllable. Same idea for a puller and a pusher engine. Safer for bailing out, yeah. If you've got a problem with aircraft and you have to either eject or sit on a jet, but jump out and parachute, if the engine's in front of you, you jump out, you go back away. Great. If the engine's behind you, you jump out, you might make a mess. Okay, we don't like that. FOD, foreign object damage, ice ingestion. Yeah, lesser chance of FOD hitting the engine than at the rear. That's always good. Warmer to flying, especially older craft. Some old aircraft are open cockpits, so the nice engine at the front, the big, nice warm engine air coming over you. Okay, it might be a bit greasy and oily, but at least it's certainly very warm. Reduced vibration from downwash, yeah, always a good one as well. Great controls, soft air due to forward mounting. They're getting the boundary layer air helping out there as well. Less weight on the controls. Reduced effects of yaw and pitch. Rear mounted can induce more power settings. So there you go, some configurations. Tractor, the pusher, you can just see the engine up on top of the fuselage behind it, little microlight aircraft there. And we've got over the wing one. Pulling it, there's that one's pushing it. Okay, let's see where before we move on too far. It's almost lunchtime, so don't go too far with it. We're just about there for that part. Yeah, so what I'll do, I'll just finish that contra-rotating one, and that'll do for lunchtime. So let's have a look at this one. So contra-rotating propellers, basically it's a propeller with another propeller behind it, but they rotate in the opposite directions to each other, so they balance each other out. Okay, driven by a single engine and caused to rotate opposite directions. Okay, so there we go. So you've got a front propeller, and then directly behind it is another propeller. Again, both of them are working in opposite directions. So the vibration, etc., should balance each other out. It's not possible to feather just one. So we can't just feather this propeller or that one. When we feather it, both of them will feather at the same time. There's no point in having one feathering and one nut. Okay, so when you go to feather position for this type of configuration, both of the propeller systems will feather together. And likewise unfeather. Okay. Okay. Right, that's as far as I'm going to go. That's lunchtime. I think it's a good point to stop there. We'll move on from lunch to propeller and spinner installation, how we fit them and the spinner installation on that one. And that will take us up to, see where we are, not too far away. Yeah, we'll finish that just after lunch, probably before the first tea break. And then we'll start on boot to give you a heads up for Monday as well. Okay, any questions before we go to lunch? Everybody happy?
Yeah.
No questions.
All good? All still alive. Yeah, I can hear the voices. That's good. It's always a good sign. Okay, guys, what's that? 20 past 1 now. Yeah, but between 20 past, half past 1 at the latest, okay, depending on times there. Well, 1:30 my time. And we'll see you back between then, okay? Enjoy your tea, and I'll enjoy my lunch. Okay, we'll see you in a little while.
Yeah. अब चियाहरू जाने चिया छुरोट
है एक्लै एक्लै ल ल ल
ए जे म सुतिसक्यो हो
आछेन आछेन
आएको अब चित्ताइहाल्छ
Hello, back again.
आयो
All fully fed and watered? Yeah, all ready to go again? Somebody else?
हामीले खाएको छौँ कि
All right. Oh, we've got full house. Got everybody in now. Good. Good, good, good. Oh, we're getting rock and roll. You've all gone shy again, guys. You're not putting your cameras on. All right. There we go. There's Sandeep. There he is. The duty hero. Excuse me. Please keep your cameras on, guys. How close are you to the camera, Pasmani?
Hello.
Hello. Came up. Yes, we've got.
Yes.
हेलो हेलो सर
Hello, hello, hello. Right, so just about 1:30 there. We've got everybody in the house. Good. All good going. So we shall continue. Hopefully, you've had enough food and water or other type beverages, tea, coffee, gurkha beer, whichever suits you. Okay, right. We're going to continue with types of propeller installation. Basically, how we're going to fit the propeller to the hub and engine as well, that sort of thing. Okay. And then we'll do a little bit of recap later on. As I say, I like to try and get as much of the theory as possible. Gives you a little bit of practice or revision Tuesday afternoon, hopefully. So this section we'll finish off, and then we'll start book 2. Book 2 is a bit more in depth, a bit more technical involved. The other half of the book is quite straightforward, thankfully. But we'll finish off book 1, and then we'll see how we get on from there. Okay, so types of propeller installation. Basically, 2 types or 2 basic ways in which propellers attach to the aircraft engine. Nice and straightforward. We've got the splined shaft attachment, and okay, so there's a splined one. Basically, the male and the female end. So the female end on the hub, and the male end obviously on the gearbox side. Again, there's your PCU and your CSU, and again, some sort of nut will secure it all. So nice and easy. Just slide on the spline, tighten it down properly. All is good. Okay, well, that's the first one, splined attachment, and then we've got the common bolt attachment one. And so basically 2 mating flanges with several bolts located together. Now back at AST, we've got a Jetstream aircraft, and that's the way the propeller's mounted to the aircraft engine. We get the students to take the propeller assembly off, do a few checks on it, and then get to put this propeller assembly back on as part of the practical tasks. Unfortunately, I can't give you guys to do that, but I'm sure you'll get a chance of that at some point. So it's the 2 main types, spline and simple bolted flange attachment. So the spline one, propeller hub is normally centralised on the shaft by what's called front and rear cones. Okay, we'll have front and rear cones. So there's your spline. Okay, and we'll have some sort of cone at the front and some sort of tapered cone at the rear. And that helps just centralise it all together to make it sure it's sitting equally spaced. Now I've colour coded these ones. Okay, so the front one is usually made of steel, not necessarily blue, they could be coloured right enough. And you'll have the front cone with the serial numbers, so this should be matching, because as you can see in the diagram here, they're actually split in 2. Okay, same with the rear there. Now, if they're split in 2 and you have 2 different part numbers, then potentially you might get a mismatch and it won't line up properly. Although they look exactly the same as a part, make sure the serial numbers are matching for the 2 parts. Okay, so the front one, tapered with made of steel normally, and then the rear one is a split in the top and usually made of brass normally. So steel at the front, brass at the rear. Typical spline propeller installation. As you can see, there's the shaft, and then you can see the rear cone. It's in the little blue segment there, and at the front cone, again, just helps line up the missed slight alignment on the splines, makes it in a perfect position. Okay, so in there you'll have obviously the mechanism, the change mechanism for changing the pitch. You'll have your leads for your de-icing systems, except the brushes and so on, and oil transfer tubes, etc. And eventually all outside, give it a nice aerodynamic coverage, will be your spinner as well. Now, flange one, straightforward. We just bolt them to the other flange on the actual engine. Various types. This one I've got here is a piston engine. So there's your crankshaft, there's the front of the engine, there's your flange, and all you do is simply bolt that to the flange. Okay. And likewise, there you go, there's a flange in red here. That would go through. There's your back plate. And then the flange on the engine, we mate together, bolt it all up, make sure you torque tight correctly, and constant instructions, and then that is it. Excuse me. So moving on with the actual aluminium propeller assembly, typically forged solid aluminium assembly. Blades are usually retained in an aluminium alloy hub by a ferrule, ball bearing, and some sort of retention nut as well. Blade root is tapered and threaded, so onto which it's screwed and shrunk a steel alloy ferrule blade retention. Just another seal. Ferrule is a seal just to make sure it sits in the right position. So the ferrule supports the inner race of the blade ball bearing, and the outer race is located by an aluminium alloy nut which screws into the actual blade socket in the actual hub itself. What you want to remember or highlight in your books is there will be approximately, depending on the type obviously, 30 steel balls and 30 plastic ball separators, just the cage that actually holds these ball bearings in. And that will complete your complete ball bearing. So approximately 30 steel balls and 30 plastic separators. Okay, and that maintains your bearing assembly. The ferrule is drilled to accept the blade actuating pin, which connects the blade to the pitch change mechanism, again through a laminated steel alloy connecting rod. It's just a bit of background on how these things are actually made together. So the retention nut is shimmed. Now we say shimmed, so it maintains the correct distance. So we can get the correct torque on there. If it's too small, it's not enough, we might not get correct torque. And that enables clearances in the blade bearing to be taken up, and so as not to put too much stress on it, and obviously not to have a gap, which could potentially be quite catastrophic. And that stops the blades from shaking about as well. Again, if the shim is too small, when we torquing the blade down, that can be too tight, so it has to be correct. It allows the blade to actually adjust without being too slack. The nut is locked by a lock ring, which is deformed at the grooves in both the retention nut and also the hub socket. Again, but we'll see this as we go on. Hub is forged aluminium alloy construction again, so this sort of aluminium alloy is used for many, many different components, not just in the piston and propeller aircraft, obviously, but various other types of components. Nice and lightweight and strong at the same time. Flange that accept blades, pitch change mechanism, and your propelling and mounting crankshaft. Now, grease is retained in the bearing by an O-ring of, say, centrifugal force. If you've got grease in there for lubrication, etc., and corrosion prevention, if you don't have a seal in there, the grease is going to get flung out, centrifugal force, and make a bit of a mess, unfortunately. Retaining nut, again, located on a ferrule by a spring steel retaining ring. And you'll have your counterweight assembly that attach the blade of ferrules, outboard, and retaining ring forward of the cambered face. Very important, the weights are matched sets. So again, if a question comes up about centrifugal weights, they must be a matched set. Each half of the set will have the same serum. Just like the front cone, the weights are also matched because they will be weighed as a match and specific for that propeller, for the balance. So again, don't just go and pick up a set of centrifugal weights and go and fit them. They have to be a set match, a match set even. Propeller balancing weights are attached to the counterweights as required. Okay, depending on, there's maybe some amendment or modification of propeller. So again, the balance weights have to be set accordingly. There's your counterweight. Okay, there's the locking ring. And you'll have your other bits of your change mechanism, so on and so on. There's the blade bearing. Again, the one that will have your 30 ball bearings in there. Again, your plastic surround. There's a ferrule which it sits in. The blade actually sits in as well. So again, you see why it's important that the nut must be shimmed to make sure it's the correct amount of torque and gap there. And just an exploded diagram of what's all going on. Okay, maybe it'll zoom in there. So there's your little O-ring going round, stops the grease and oil coming out. There's the green part there, which is the ferrule it's screwed into. And again, you can just see the ball bearing and all the mechanisms that help it move about. Again, that's just an exploded diagram. We'll break these down into more specific components. Oh, got some dogs coming in. Questions? Again, that's just an exploded diagram of what you might see if you actually take it all apart. There's your brush gear selectors, your spinner back plate, okay, the hub assembly itself, operating control links, front cones, again, you have the rear cone, etc., etc. And there's around here is your brush box. That's your little connection box, which will go onto your, have a little connection to carbon brushes to provide you electrical power for anti-icing, etc. Other components you might have, have electrical hydraulic switches, back plates, pistons, cylinders. It all depends, excuse me, on the type of assembly you've got. Again, we'll look at this more in depth. This is just a little insight of what you might see if you take one apart. This one, we've got obviously the main core engine here. It's been split about. There's the turbine at the back. Again, you've not done module 15 yet, but hopefully you'll recognise some of these bits. So the turbine in the back. We've got two compressors here, which are centrifugal type compressors. A little gear on the shaft, so as it's rotating, it's going to spin the gearbox, which the gearbox will have components like fuel pumps, air conditioning, whatever, all that sort of thing, oil pumps, etc. Again, there'll be a reduced gearbox ratio. And this one's got starter motor shafts. There'll be a starter connected to this bit through a bevel gear, which will rotate the shaft. And then we come to the reduction gear housing for the propeller, which will also have the torque meter. Members spoke about the torque meter systems yesterday. The hydromechanical and the electrical, and this is the hydromechanical one, just an example. And you can see some off takes. We've got another bevel gear here, which will be attached to the gear on the shaft. Again, another bevel gear. Bevel gears allow transmission at different angles. And there's an oil pump as well, fuel pumps and so on. Again, this is just an explosion of a type of engine. So in the main core engine here, attached reduction gearbox at the front, and then also you attach on your spline connection, in this case, your propeller assembly. Okay, so it's an exploded view. So typical spinner installation, you check the spinner bulkhead for any signs of damage. No point in putting things on for the damage. Usually things a bit of stress in the front of the aircraft, front of the engine, so prone to potential damage. So things like cracks, distortion. You will coat the inner seal with an approved lubricant. Don't just pick any lubricant up, because some lubricants can actually damage the seal. So in accordance with your instructions, and install it onto your dome assembly. Install the spinner. Now, when you're putting a spinner on, whether it's a gas turbine engine or a turboprop engine onto a propeller, make sure they line up. Now, some spinners will have a little pin, so it can only go in one position. Some spinners you can take off and rotate around, and that can help with balancing vibration problems as well. If you're taking a spinner off and going to be put back in the same engine, it's as well, if you don't have an indentation, actually mark it up with a bit of masking tape or something, but don't write with permanent marker on the end. So it's the same part going on, mark it off so you take it off, you know exactly where it's going on before. Again, when you're refitting anything, torque loads, apply your torque wrenches correctly, make sure you get the right numbers in there. Big torque wrench, big bolt, small torque wrench, small bolt, okay? We do have it with the students, we teach them how to torque wrench, and occasionally we get the ones that break things just by thinking they know what they're doing, and we make sure, but better to learn by mistakes in the train environment than it is on the real place. I'm sure we've all had shots of torque wrenching, and everybody will get it wrong at some point. The difference between pounds feet and pounds inches, easy to get mixed up, but hopefully you're all good engineers. So a basic explode diagram again, there's your spinner. So it is possible to potentially put a spinner on at different positions around the hub assembly, but normally there will be a locating pin or locating dowel which will keep it on the same place. Some do, some don't. Okay. Again, just an exploded view of where it will be. Some sort of support, and then the casing itself will just locate onto maybe drillings around the back plate here. Okay, just various different ways of doing it. And once it's all assembled, you can see the assembly inside and your back plate and anything else that needs to be attached to it as well. And all we're doing, the spinner acts as a nice aerodynamic front to the hub for the propellers, keeps things nice and smooth, and stops dirt and other parts and pieces getting in there as well. All right, so we've got another set of questions, page 113. Again, do those on your own time. We'll get a break or over the weekend. So it's a couple of pages you'll have to do of questions. And they are in order of the book, so they're almost word for word within the paragraphs of the book, so hopefully you'll be able to fill in the blanks. Again, we will go through these on Monday morning. I'll put the questions up on the screen with the blanks, and we'll put the answers in as well, just to make sure you've got the right ones. Okay. If you are doing them, hopefully you will be doing them, it's a good idea to put the page number beside the question as well, and it gives you a quick reference if you get stuck. Okay, so 10 questions there. But for the moment, that is it. That is book 1 completed. Okay, so not too bad at all there. Not passing in. It's about a day and a half thereabouts per book. That'll give us half day today, a full day on Monday, and a little bit of Tuesday morning, just in case we have to go over a little bit. And then, as I say, Tuesday afternoon, we'll try and do as much revision questions with you as possible, give the best chance for your exam. Okay, 32 questions of fun, as they call it. Okay, any questions on what we just covered there? Nice, straightforward, hopefully, nothing too taxing. Everybody happy there? Yeah, all good. Right, give me a couple of seconds. I will get book 2 up and running. Remember where to put it. Two. 2 seconds. Okay, there we go. So on to book 2 now. I'll just check that. All right.